Hello friends, this is our last lecture on the first unit. Okay, so today our first unit Riemann integral will be over. In the last lecture, we have started with the integral as a limit of sum. We have seen the concept. Okay, now we will solve some example on the integral as limit of sum. Okay. The first example is to show the integration of the function x square from a to b is equal to the 1 by 3 b cube minus a cube. And this we have to solve by expressing definite integral as limit of sum. So that we have directly given the solve this by using integral as limit of sum. Okay. Now here our function is f of x is equal to the x square. Now this function is continuous everywhere in R. So this function is continuous on the interval AB. Okay, so it is continuous. Polynomial function is always continuous. So function f of x is equal to x square is a continuous function. So this implies the function f is Riemann integrable on this interval because every continuous function is always Riemann integrable. We have seen, okay, we have seen this criteria. So this one implies this function is Riemann integrable on the interval a to b. So we know the formula for integral as a limit of sum. If function is integrable, then integration of the function. So here integration of the function f of x. Here f of x is x square, and integration is from a to b is equal to the limit n tends to infinity h into summation of f of a plus kh. The summation is from k is equal to 1 to 0. Okay. This is the integral as the limit of sum. Okay. Now, and where h is nothing but where h is equal to b minus a upon here. Okay, this is the value of h. Now we will solve this part to get the integration of our function x square. Okay, so now this is equal to limit n tends to infinity. This h and this. Okay, now summation f of a plus kh. Now the function is defined as f of x is equal to x square. So f of a plus kh will be equal to a plus kh whole square. Okay. This implies this value of f of a plus kh will be a plus kh whole square. Why? Because function takes value to its square. F of x is equal to x square. So f of a plus kh will be square of a plus kh. Okay. Since f of x is equal to x. Now we will take this. We can solve the square bracket. Okay. So we can solve the square of the addition of two numbers. Okay. This will be equal to limit n tend to infinity h as it is summation. We know the square of a plus b whole square, a square plus twice ab plus b square. So here this is a, this is b. So the square will be equal to a square plus twice a k h plus k square h square. Okay. Now hereafter we will put value of h because h involves n, so we have to put value of h. Okay. So now this is equal to limit n tends to infinity. Value of h is b minus a upon n. So b minus a upon n in bracket. Okay. So here a square summation of, we will separate summation also, summation a square. Since summation is on sum of three elements, we can separate the sum. So summation of a square plus twice ah twice a, h value of h is b minus a upon n into k. So sum will be on k only into summation of k, and k varies from 1 to n. Okay. Plus, so h square we can take outside the sum because sum involves only terms of k. So plus, right here, so plus h square, so b minus a whole square upon n square into summation of a square. Okay. So now this will be equal to limit n tends to infinity. Okay. So this b minus a upon n as it is. Now again, here only the terms of s, there is no term of k. Okay. So we can take this a square outside and sum will contain only 1. So sum of 1 from k is equal to 1 to n. Because a square is constant, so a square into 1 is a square. So sum will only the term 1 and sum of 1 n times. Okay. So this sum of 1 n times will be equal to n. Okay. So 1 plus 1 plus 1 up to n times, so is equal to n. So this sum will be equal to a square into n. A square as it is, and sum of 1 n times will be equal to n plus twice a. Okay, is as it is, twice a into h. So b minus a upon n, and sum on k, and k is equal to 1 to n. That is sum of first n natural numbers, and we know the formula for finding sum of first natural numbers. So the formula is equal to, so this twice a into b minus a upon n as it is. Then this sum is, we know the sum is equal to n into n plus 1 upon 2. So next term we write in here. So plus b minus a whole square, okay, upon n square, and summation of square of first n natural number. We also know the formula for finding sum of square of first n natural number, and the formula is n into n plus 1 into twice n plus 1 upon 6. Okay. Now we'll find the limit as n tends to infinity. Okay. So we have come up to this step. Okay. Now we will take this n inside the bracket. Okay. So due to this n and this n will get cancelled. Okay. Because this n will be in division with each term. Okay. So we can write this is equal to limit n tends to infinity, this b minus a as it is. Okay. So we have taken a inside, so this n and this n get cancelled. So in bracket here remain only a square plus, here we can write twice a into, now these two also will cancel, these two and these two. So here a into b minus a into n plus 1. This n already get cancelled. So n plus 1 upon n plus 1 upon n. But we can write this as n by n plus 1 by n. So n by n is 1. So we can write this as n by n. So 1 plus 1 by n. So plus 1 by n. Okay. So plus this b minus a square as it is. Now this here it is 6. Okay. So we can write, so this n will already get cancelled. So divide this n square with the terms n plus 1 into twice n plus 1. So n plus 1 into twice n plus 1 upon n square. So this becomes n plus 1 into twice n plus 1 upon n square. Okay, so we can write n square as n into n. Okay, so this can be written as n plus 1 upon n into twice n plus 1 upon n. Okay, again from this we can take two outsides. Okay, so this become again same as this n by n. So separated denominator. So n by n is 1 plus 1 by n is 1 by n. So this become 1 plus 1 by n. Okay, now here it is twice n plus 1. Okay, so twice n upon n is 2 plus 1 by n. So this also becomes twice n upon n. So 2 plus 1 by n. So 2 plus 1 by n. Okay, so twice n plus 1 upon n. Twice n upon n is 2 plus 1 by n is as it is. Okay, so this is we have some make some arrangement or some adjustment here. Okay, now apply the limit as n tends to infinity. Okay, so as n tends to infinity, this 1 by n tends to 0, this 1 by n tends to 0, this 1 by n tends to 0. Okay, so here 6 is remaining, so 1 by 6 as it is. Okay, so what will you get? So this b minus a as it is. So inside the bracket, this a square as it is, this a into b minus a as it is. So as n tends to infinity, 1 by n tends to 0. So 1 plus 0, 1. So 1 into this a into b minus a, plus this b minus a square as it is. Okay, so as n tends to infinity, 1 by n tends to 0. So this is 1. Okay, this is 1. This upon 6 as it is. As n tends to infinity, 1 by n tends to 0. 0 plus 2, 2. 2 into 1, which is equal to 2. And this 2 and this 6 here. 2 into 3, 6. So this becomes b minus a square upon 3. Okay. Now take this 1 by 3 common, but here there is no 1 by 3, so we have to multiply this term by 3. So 1 by 3 we will take it outside. 1 by 3 into b minus a. Okay, you have taken outside. Okay, so this become thrice a square. So since here there was no 1 by 3, you have to multiply this term by 3. So 3a square plus 3 into a. So multiply this term also by 3 and multiply thrice a with b minus a. So this becomes thrice a into b minus thrice a into a. So thrice a square plus this 1 by 3 already taken outside. This becomes b minus a square. Okay, now we will add these terms. This will become 1 by 3 b minus a into the bracket. This thrice a square and this minus thrice a square get cancelled. Okay, this is, now we will take the square of this. Okay, this thrice ab as it is, thrice ab as it is. So here square of b minus a whole square. Okay, so the square of b minus a will be equal to, so plus b square minus b square minus twice ab plus a square. Okay, plus a square. Okay, so b minus a square is equal to b square minus twice ab plus a square. Okay, so this is equal to 1 by 3 b minus a as it is into, so this thrice ab minus twice ab will be equal to only 1 ab. So we will write for a square, or say we will write say b square as it is. This thrice ab minus twice ab will be equal to 1 times ab, so only ab and plus a square. Now see this term b minus a into b square plus ab plus a square. What is this? This is nothing but the formula of b cube minus a cube. This will be equal to the 1 by 3 b cube minus a cube. If you multiply, you will get b cube minus a cube, because b cube minus a cube we already know standard formula b minus a into b square plus ab plus a square. So the integration of a to b of the function x square is equal to 1 by 3 into b to minus a. Okay. So next example, based on integral as a limit of sum. In this example, we have to show the integration of e raised to power x from a to b is equal to e raised to power b minus e raised to power a. In general, we know that this integration of e raised to power x is from a to b e raised to b minus e raised to power a, but we have to solve using integral as a limit of sum. Okay. So the function given is here f of x is equal to power e raised to power x, and we know this exponential function is always continuous on the any interval of real numbers. Actually, it is continuous or whole R. Okay, so it's continuous everywhere. So it's continuous on any interval from a to b. Okay, this implies here is Riemann integral on the interval a to b. So we can use the formula for integral as a limit of sum. Okay, the formula for integral as a limit of sum is the integration from a to b of e raised to power x dx will be equal to limit n tends to infinity. Okay, limit n tends to infinity h into summation k is equal to 1 to n f of a plus h, where h is equal to b minus a upon n. But now see, as n tends to infinity, b minus a upon n will tend to 0 because b minus is constant, and then our n is tending to infinity, the value is going to 0, that is h tends to 0. So instead of writing h tend to infinity, we can write h tend to 0, because n tends to infinity means this value goes to 0, that is h tends to 0. So n tends to infinity is same as h tends to 0 in this case. Okay, now this is equal to limit h tends to 0. So h as it is. So here we don't have to need to replace h as b minus a upon n, because we are directly solving in terms of h, and summation k is equal to 1 to n f of a plus kh. F of x is equal to e raised to power x. So f of a plus kh will be equal to e raised to power a plus kh. So since f of x is equal to e raised to power x, so f of a plus kh will be equal to e raised to power a plus kh. Okay. So this is equal to limit h tends to 0 h as it is. Okay. So e raised to power a plus kh, we can write this as e raised to power a into e raised to power kh, and this summation, but summation is on k, we can take this e raised to power a outside. Okay, so h as it is, then e raised to power a as it is, and summation from k is equal to 1 to n on e raised to power kh. Okay, and k varies from 1 to n. So this is equal to limit h tends to 0 h into e raised to power a in bracket, put k is equal to 1, so e raised to power 1h, so h plus due to sum add. Okay, put k is equal to 2, so 2h, that is e raised to power twice h, up to last put k is equal to n, so e raised to power nh. Okay. Now, see, we can take e raised to power h common from each of the term. Here e raised to power h, here e raised to power twice h, up to e raised to power nh. So e raised to power h we can take outside. So this will be equal to the limit h tends to 0. This h and e raised to power a as it is. So h e raised to power a as it is, and take e raised to power h common from this. Okay. So e raised to power h we are taken common. So inside bracket it remains. So e raised to power h is common. So here given 1 because e raised to power is taken outside. Here it is e raised to power twice h. Okay, and e raised to power h 1 e raised to power h taken outside. So 1 here remain only 1 e raised to power h. Then e raised to power here Previously it will be equal to e raised to power twice h, but one e raised to power h is taken outside, so it will be e raised to power twice h up to so on. So at last e raised to power, here it was nh, but e raised to power h is taken common, so it will be at last e raised to power what, n minus 1 h. Okay, now see, this is the geometric series with common ratio e raised to power h. Okay, this is nothing but the geometric series. This is n minus 1 h. This is nothing but the geometric series. Okay, e raised to power n minus 1 into h. This is geometric series with common ratio e raised to power h. And we know formula for geometric series: summation of x raised to power n or x raised to power k minus 1 is equal to 1 to n is equal to 1 minus x raised to power n upon 1 minus x, or x raised to power n minus 1. Okay, x raised to power n minus 1 upon x minus 1 for the series x raised to power n. So here this is the geometric series with common ratio e raised to power h. Is with common ratio e raised to power h. We know the sum of the series or geometric series with common ratio x, okay, is equal to the x raised to power n minus 1 upon x minus 1. Okay, so this will be equal to the limit, this is equal to the limit h tends to 0, this h into e raised to power a into e raised to power a as it is, and this will be equal to e raised to power, so x raised to power n, here x is e raised to power h, so e raised to power h raised to power n, so e raised to power nh minus 1 upon x minus 1, so upon x is here e raised to power h, so e raised to power h minus 1. Now we will apply limit. So here e raised to power a is constant, so we can take it outside. This is equal to e raised to power a is outside into limit h tends to 0. This h as it is, this e raised to power h as it is, upon this we can take this denominator e raised to power h minus 1. Okay, so upon e raised to power h minus 1, but here e raised to power nh, the value of h is b minus a upon n, so b minus a upon n into n, so n and n get cancelled, so remains only b minus a. See, n h, n value of h is b minus a upon n, so n and get cancelled, so remains only b minus a. This implies e raised to power in bracket e raised to power b minus a, this minus 1 as it is. So this is equal to e raised to power a as it is. Now we will make some adjustment. So here it is h, so limit h tends to 0, this h as it is, upon we write this denominator e raised to power h minus 1, because we know the limit of h tends to 0, h upon e raised to power h minus 1. This e raised to power h as it is, and this e raised to power b minus a minus 1 as it is. So now this is equal to e raised to power a. The limit at h tends to 0 of h upon e raised to power h minus 1 is 1. So into 1. Again h tends to 0. Then e raised to power h tends to e raised to power 0, and e raised to power 0 is equal to 1. So it is 1. So e raised to power a into 1 into 1. So it is equal to e raised to power a, and this in bracket e raised to power b minus a minus 1 as it is. So e raised to power a, multiply this e raised to power a inside the bracket, this will become e raised to power a into e raised to power b minus a minus e raised to power a into 1, so e raised to power a. Now e raised to power a into e raised to power b minus a, so e raised to power a into e raised to power b into e raised to power minus a. So here we can write this like e raised to power a e raised to power b into e raised to power minus a. So e raised to power a e raised to power minus a becomes e raised to power 0, which is equal to 1. So 1 into e raised to power b, so is equal to e raised to power b and minus e raised to power a. So integration of a to b e raised to power x dx will be equal to e raised to power b minus e raised to power e using integral as limit of sum. Okay. Last example based on integral as a limit of sum. Okay. So after this we will cover unit 1, that is Riemann integrable functions or Riemann integral. Okay. So using the property of limit of sum as a definite integral, so that limit of this quantity is equal to log of 2. Now here the idea is to write this series or this sum as a standard sum. Okay, so we have to be able to write this as a sum of this like summation of some functions. Okay, then we know limit of sum is equal to integration of that function. Okay, so we try to write this in a standard form. Okay. So now limit n tends to infinity of 1 by n plus 1 upon n plus 1 plus 1 upon n plus 2 up to 1 upon twice n minus 1. That is, we can write it n plus n minus 1. So n plus n twice n minus 1. Okay. Is equal to limit n tends to infinity. We will take 1 by n outside. So 1 by n. So here first element will be only 1 because you are taken 1 by n outside. So here there is no 1 by n. So we have to make some adjustment. Okay. So we will write this as, okay, so 1 upon n plus 1 upon n. Okay. Why write in the denominator 1 by n? Because this one, if we have write here 1 by n, we have taken 1 minus common, but here there is no 1 by n, so we have to make this adjustment. Okay. So if 1 by n taken inside, so 1 by n into 1 will be 1 by n. 1 by n into this will be this n, and this will get cancelled, so remains only 1 upon n plus 1. So for this we also make some arrangement. So we have to divide this term by n, so that we can take 1 by outside. Okay. So again in third term there will be 1 upon n plus 3 upon n up to so on. At last 1 upon n plus n minus 1 upon n. Okay. So this is nothing but this. Just we are taken 1 by outside and make some arrangement. Okay. Now see, we can separate the denominator. This is equal to limit n tends to infinity 1 by n into 1 as it is. This is 1 upon n by n is 1 plus 1 by n, so plus 1 by n here. So here it is 2. Okay. So after that here 1 upon n by n is n, so 1 plus 2 by n. Okay, plus 2 by n. Continuing this way, at last it is 1 n by n is 1 plus n minus 1 upon n. Okay. Now see, we can write this sum in summation notation, because here we observe there is some standard formula. See, summation 1 upon 1 plus k by n. Put k is equal to 0 to n. Now this is equal to limit n tends to infinity 1 by n as it is, and summation where is form k is equal to 0 to n minus 1, and sum is taken over 1 upon 1 plus k by n. See, if you put k is equal to 0, the 0 by n will be 0. So 1 plus 0, 1 upon 1 plus 0, that is 1 by 1, it is 1. Then put k is equal to 1, so 1 upon 1 plus 1 by n, 1 upon 1 plus 1 by n. Put k is equal to 2, 1 upon 1 plus 2 by n, 1 upon 1 plus 2 by n. So we get some standard summation formula. Okay. So to this is our function. Okay. So this is nothing but equal to f of k, where f of k is equal to 1 upon, so this is equal to f of k k by n. Okay, where f of k by n is equal to the 1 plus 1 upon 1 plus k by n. This is our function f of k by n, and it is equal to 1 upon 1 plus k by n. We have seen if you put k is equal to 0, you will get to 1. If you put k is equal to 1, so 1 upon 1 plus 1 by n. This, so we get a function f of k by n such that f of k by n is equal to 1 plus 1 upon 1 plus k by n. That is f of x. If you call k by n as x, it is equal to 1 upon 1 plus. So instead of k by n, just write x. So 1 upon 1 plus x. So this is our standard function. Okay. So from this is limit of sum, and we know the formula for integration as limit of sum. And this sum varies from 0 to n minus 1. This means integration is from 0 to 1. We know, we already seen the formula. This implies this is equal to the integration from 0 to 1 of f of x, and f of x is 1 upon 1 plus x is equal to 0 to 1 upon 1 plus x dx, and 1 upon 1 plus x is continuous on the interval 0 to 1, so it is integrable. Okay, so this is equal to integration of 1 upon 1 plus x, we know it is integration of 1 upon 1 plus x, we know its integration is log of 1 plus x, so this is equal to integration is equal to log of 1 plus x, and limits from 0 to 1. We can evaluate this integral because this function 1 upon 1 plus x is continuous, and so Riemann integral on 0 to 1. This is continuous function on 0 to 1, and this is equal to, put x is equal to 1, so this is, so we can write log to the base e. So just write ln, that is log of, put x is equal to 1, so 1 plus 1 is 2, minus put x is equal to 0, so 1 plus 0 0, so log of 0, so log of 1 plus 0 is, put x is equal to 0, so 1 plus 0 1, so this is equal to log of 2 minus log of 1, but log of 1 always equal to 0, so equal to log 2. So limit of this is equal to log 2. This is the application of integral as a limit of sum. So thank you. This is the end of our unit 1, that is Riemann integral functions, or just Riemann integration. Okay, so all the best to you. Study this unit properly. If there is any doubts, please ask me. Okay, so stay safe, stay home.